Hi, and welcome to the second part of our video series on making sure that you get the A star in the Cambridge iGCSE exam for chemistry. And the first video actually took us through the first 11 questions in the multiple choice questions that we are tackling in the series. We've got 40 in total. And the great thing about this, and what I hope makes this series a little different, is that I've already tested 50 iGCSE students with this, and I've got a full range of expected answers, and as well as that, the most common mistakes that people actually make. So we will go through all of the questions. You'll have time to pause the video if you wish to answer any of the questions, and we'll go through everything step by step as a walkthrough. So let's have a look at this question number 12. It's to do with environmental chemistry and the air. Catalytic converters in car exhausts change polluting gases into non-polluting gases. Now, this is one of those questions where you have to read the statements and then you have to figure out which of the statements is correct in this situation. It's always worth having a look at the question, because sometimes they ask you, should your responses be correct, or your responses need to be not correct or false. In this question, it is correct. So pause the video if you wish to have a go at this question yourself. Okay, right. So the statements about oxides of nitrogen and car engines. So essentially, there is quite a little bit of misconception about where the actual oxygen comes from. People sort of think and confuse this with fuel cells, and they think that maybe oxygen comes from water. But it's all about knowing what this part of the specification is all about. It is factual information. So here is a not very good representation of a car. So here we have a vehicle with the headlights, and you've got the bonnet there, and you've got boot there. Right. So it all seems to be happening in the car engine itself. So if we look at this section over here, inside there, you actually find obviously the engine, and inside the engine, you have very, very high temperatures, extremely high temperatures. Now, the engine is combusting all of the fuel inside there, all of the octane, or perhaps it's diesel. Now, if that is the case, you have high temperatures, and you actually also have air within the internal combustion engine, because the fuel needs to burn in the presence of oxygen. So you actually do have air in. And that air contains nitrogen, and it also contains oxygen. Now, the science behind this is that the nitrogen and the oxygen combine together to form a series of various compounds, which we put under the category of NOx, NOx, because you actually do have a variety of different nitrogen oxides. Some of them are dioxides. There's got monoxides in there as well. The danger, in terms of environmental impact and why this is polluting, the danger is that if this actually is combined with water, which obviously you get from the air, water vapor, from clouds, and also rain, precipitation. If the nitrogen oxides dissolve in water, you actually form nitric acid. So don't forget that nitric acid is an acid that you should be familiar with. So the nitric acid can then have an impact as acid rain. So that's pretty much the theory behind it. Now, the additional thing as well is that before the car emits the exhaust nitrogen oxides, you've actually got this little chamber underneath called a catalytic converter. Now, that catalytic converter is full of very precious materials, for example, platinum. And what actually happens in this honeycomb type of environment is that the nitrogen oxides land on there, and they rearrange themselves back to form harmless gases that can then be emitted, some of which are nitrogen and oxygen. So you've actually got a situation here now where you have enough information to progress through the question. So we're looking for correct ones. The nitrogen in oxides of nitrogen comes from compounds in petrol. Well, clearly that's where the false part is. You've got the oxygen in oxides of nitrogen comes from the air, so that is correct. And catalytic converters convert oxides of nitrogen into nitrogen and other gases, which is also correct. So as a result of that, we've got response 2 and response 3, and that means that this is the correct response to give. So do have a chat if you have a chance, and you need to make sure that you read up on catalytic converters and the fact that they use precious metals like palladium and platinum. Do get to know the equations that actually take place in the catalytic converter. So you've got the NOx molecules that turn to nitrogen and oxygen. You've got carbon dioxide and oxygen. They combine together to form carbon dioxide. And any hydrocarbons that are in there are converted to carbon dioxide and water. So now we're going to move on to our next question. The next question is an equation that represents an equilibrium in aqueous ammonia. So if you wish to pause the video, you may do so. So, so this question over here is talking about an equilibrium. So it really does make a difference if you have covered equilibrium in your classes. It's usually a year 11 topics taught very, very late on, well past year 9, where you would kind of expect students to be taught about acids and bases. So it's a really good question for the example to come up with, because it links a year 11 set of ideas with a year 9 set of ideas. It's very, very, very sneaky of the designers of this question. So how does aqueous ammonia behave in this reaction? So you've got aqueous ammonia over here on the left-hand side as one of the reactants. So there's your aqueous ammonia, and you notice that you start off with 3 H's on the ammonia, and now it actually becomes something that's slightly new now. The extra H has now caused a charge to form. So you're not actually adding a hydrogen atom to your ammonia, but you're actually adding a hydrogen ion to the ammonia. So in a similar way, look at what's actually happening with the water. So you start off with HHO, and then, or H2O, depending on how you want to say it, and you end up with H and O, but overall, you've now got a negative charge, and the reason why is because H plus proton has actually been lost. So it's actually been lost from that original water in order to form the ion on this side, which is the hydroxide ion. So you've got a situation here now where I believe you've got enough information, so you can actually now realize that a H plus has now been donated to the ammonia, and so the ammonia is actually acting as a base. So you can immediately cross out A and C. Now, that takes you as far as 2 choices. Now, you've got to try and figure out whether it's a strong base or a weak base. A strong base is very, very good at accepting protons, in the same way that strong acids are very good at dissociating and donating protons. We don't actually have that situation here, because the ammonia would like to the ammonia would like to actually go backwards in this reaction, we can see. So the ammonia has ammonium ion has a tendency, this ion over here, the ammonium ion, I have to make it very clear. This ammonium ion has a tendency to dissociate back and lose its extra proton. So if we come back to the ammonia, if it actually accepted the proton from water as a base, it would not want to revert back to the original ammonia, or to put it another way, it's reluctant to actually accept the proton from water. It will want to go backwards. So the answer to this question is D, as a weak base. So let's move on to the next question. And while you're giving a read on that next question, you'll be pleased to note that that previous question, if you were a little bit stuck on question 13, so were roughly around about 60% of our sample. And the most common mistake that was picked was actually choice A as a strong acid. But choice D was picked by the majority, around about 40 to 41%. Around about 30, maybe almost a third of candidates actually pick A, and around about a quarter of candidates in our sample picked B. Very, very few people actually picked C. So let's get to this one, and immediately you'll be forgiven for thinking that this question 14, is a tough one because it starts off with something perhaps a little bit unfamiliar compared to other chemicals that you could actually just be asked about. It starts off with chloric 1 acid. So I'll let you read that. Pause the video if you need to. So chloric 1 acid actually has a formula, and the first thing that you ought to do is you ought to make sure that you read the actual formula correct. Don't mistake that HCl for something like HCI. Chloric acid, chloric 1 acid to be specific, it's formed when chlorine dissolves in water, and it is a weak acid. So this question is actually expecting you to come up with weak acid, and hopefully you have learnt the definition that's stuck in your mind. The answer to this question was picked up by almost 3/4 of our samples. So it is actually a question that that is very well answered, very well responded to. However, the most common mistake that's actually picked up is A. So you'll get around about between 15 to 20% of candidates actually picking A. Now, people pick A because they associate weak with fewer hydrogen atoms. Now, you have to be really, really careful about that because there's so much wrong with that sentence. For a start, an acid does not contain hydrogen atoms that are donated, but it's actually H plus ions, hydrogen ions, protons. So the second thing is that there are definitely certain acids that you can come up with that actually do only contain, they actually contain fewer hydrogen ions that can actually be donated than the corresponding weak acids. So what do I mean by that? Well, I'll just run through a couple of acids just to demonstrate that. So we've got CH3COOH, that's ethanoic acid, and it's that H that that is donated by ethanoic acid. Another name for ethanoic acid is vinegar. You've got HCl, hydrochloric acid, should be familiar with that. And here's another one, H2SO4. Now, arguably, it's really is, it's really is the one of the two hydrogens that donates first, but you can actually force both hydrogens off eventually from sulfuric acid. Nevertheless, have a look at that. You've got a source of 2 hydrogens as ions. You would, by the logic of what's being explained in choice A, you'd kind of think, well, maybe sulfuric acid is twice as strong as hydrochloric acid. Well, that's simply not the case. In a similar way, you'd kind of think, right, okay, well, if we just ignore this part of the molecule of ethanoic acid, because that's not necessarily important, that's just an organic structure. In ethanoic acid, you have one hydrogen that is that can be donated by that acid. You've actually got only one hydrogen in HCl that can be donated when it acts as an acid, but the hydrogen in HCl can actually dissociate from the chloride part of hydrogen chloride when it's dissolved in water very readily. Whereas the hydrogen in ethanoic acid is reluctant to leave, and it kind of tends to want to stay behind. So you've actually got a little swap and swap back happening over there. So A is definitely not a healthy choice for you to choose. It is the easily neutralized by a strong acid. Well, strong alkalis are relatively easily neutralized by strong alkalis because strong alkalis have a source of OH minus ions that can react with H+. So that's a very dubious one there. It is less concentrated than a strong acid. It's a big fallacy that weak acids are acids that are diluted. No, you can actually get very concentrated weak acids. You can get diluted strong acids as well. So there is such a thing as strong and the opposite is weak. There is such a thing as dilute and the opposite is concentrated, and both are mutually exclusive. So the right answer is D. It's only partially ionized in solution. The reason why it's only the reason behind this answer is that partial ionization means that you have very few, if any, relatively speaking, hydrogen ions that are actually supplying this. It's healthy to consider a weak acid as potentially being an acid, but pretty much the hydrogens actually stick onto the molecules. If you want to think of it like that at this stage, then there's very little wrong with that idea. In comparison to a strong acid, which will split up very quickly to donate protons, hydrogen ions to an acceptor. So off we go to the next question. So we're going to move on. And we've got another acid question, which is as follows. So if you would like to pause the video, you can do so. So this question over here, and looking at the sample of students that actually were tested with these questions before the video was done, 41 out of our sample of roughly 50 actually got this right. So it's more than 4 out of 5 actually hitting this, and answer C is actually the most popular mistake, but roughly 10% actually pick answer C. So we've got concentrated hydrochloric acid is a strong acid, and when you read this, you should automatically think strong means that it donates and dissociates very easily. Okay, so it splits up and donates that proton. Now, the fact that it's an acid means that it's a donor. Okay, so we can immediately disregard 2 of those answers. Strong means that it is fully ionized. Fully ionized means that it's fully dissociated. Okay. So if it's fully dissociated, both these ones are wrong. The correct answer with both of them absolutely right is answer D. Okay, so we'll move on to the next question now. Give you a chance to read the next question. You may pause the video if you wish. So the next video is, the next question is actually a question that was very successfully done. So you cannot bank on on other people getting this wrong in the exam. That's the message that I want to put across. People will be going into the exam and learning the meaning of the word amphoteric. Amphotericity means that it can behave as an acid as well as a base. Aluminium oxide seems to be the one that sticks in the mind. So try to make sure that you do remember that fact. From our sample, we actually had 92% of the actual sample remembering that aluminium oxide is amphoteric. Right, very quickly, we are going to go on to the next question. By the way, carbon monoxide is neutral, sodium oxide is basic, and also calcium oxide is basic as well. So, salt. Question next. So we're going to stick with the theme of acids and bases, but we are going to tackle question number 17. So pause the video if you need to. So salt is made by adding an excess of an insoluble metal oxide to an acid. It's a very classic demonstration that you do need to understand. So effectively, this experiment comes time and time again. It sometimes lives in paper 6, sometimes it appears in paper 2, and sometimes it also comes about in paper 4. So this is something that hops from all 3 papers, across all 3 papers. Start off with typical metal oxide, for example, copper 2 oxide. And what you would do is you would add it to some acid. Now, the acid would actually be warmed. So you would actually add the acid on a Bunsen burner with a tripod and gauze and a heat-proof mat, and you'd have a source of heat. And then what you would do is you would have a glass rod, and you would slowly, once it starts to heat up to boiling point, you would actually start to spoon in that copper oxide. Now, inside is sulfuric acid. So you would heat up sulfuric acid. That's your acid there. The chemical reaction will actually make blue copper 2 sulfate. So once the oxide has reacted, this is a metal oxide, it actually form water and copper sulfate. So the idea is to try and, when you're doing this experiment, the idea is to try and make the pure salt. Now, if you keep on adding the copper oxide, eventually the acid will be used up. So you will use up the acid. That's what they mean by adding an excess. So once you do that, you can filter your mixture. Once you filter the mixture, you will then find that you'll be able to filter off any excess copper oxide. So you use filter paper. There we go. Just about got it. And put it in a conical flask while it's still warm. You have to do that step a little bit carefully. Use paper towel wrapped up carefully around the neck of the conical flask. And then what happens is you actually get this blue copper sulfate aqueous solution. And what you then do is you transfer it back into what's known as a crystallizing basin. So you put the crystallizing basin on top of a gauze, on top of the tripod. You got your heat-proof mat there as well, and you heat it. And the rough guide is roughly around between 1/4 to maybe 40% of the actual liquid that you have poured in there. What you need to do is you need to heat it and evaporate the water. So once you heat it, the water starts to evaporate, and you get to a stage where the solution becomes really supersaturated. Because if you're removing the solvent, the solubility is high when you have warm liquids. So if you have something like warm water, it's going to dissolve more of the copper sulfate inside it. But if you're then starting to remove the water, you're going to get to a threshold where where if you then started to cool it down, the solubility decreases, the solubility of your salt, and as a result, what then happens is that the salt cannot stay dissolved in the water, so it comes out as solid crystals, and they start to settle. And so therefore what you can do is you could, if you wanted to, you could filter them. It's really important that you don't take too long doing this, because if you actually heated it to dryness, you would not get crystals. You would actually just get a powder, and then eventually be an anhydrous powder as well. In this case, it would turn white and stay as a powder. So once you actually have removed around about 30% of the water, then you just stop heating. So minus 30 as a rough guide. And then what you can do is you can filter it back. And what you end up with are blue crystals. And those blue crystals can be patted dry using a paper towel. Don't forget that last point. It can be patted dry using a paper towel. And you can then obtain your dry crystals of copper sulfate. So pat it dry inside a paper towel and you're fine. Now, that's pretty much it for that experiment. We go back to the actual question itself. The question suddenly looks really, really easy. How is the excess metal oxide removed from the mixture? The answer is filtration. Now, 82% of my sample chose that one. The most common mistake, believe it or not, was actually distillation. Perhaps that was thought of because that actually requires heat, and filtration may have looked to be a little too simple for a GCSE question, but it's actually a really, really, really important separation technique to have. So we're going to look at the next question now. So if you need to pause the video, pause the video. So let's have a look at question number 18. So question number 18 consists of two parts. The first part is designed to try and trip you up. If that doesn't work, then it's the second part. And there's a really sneaky little extra bit of detail in the third sentence as well. Now, it really does help if you do know what precipitates form when you add sodium hydroxide and also ammonia. That's obviously key to this question. There is a lot of information that you have to learn, but I would tend to try, if you have to do this, I would try to encourage you to leave something like precipitation reaction information as one of your last topics to revise, so that actually stays in your memory. You could try and use different color pencils or pens to help you remember the different colors that actually come out, and shapes if you want to then think about precipitate. So we've got aqueous sodium hydroxide reacts with an aqueous solution, so we don't know what this aqueous solution is. It's compound Y, whatever that is, to give a green precipitate. Aqueous ammonia also reacts with an aqueous solution of compound Y to give a green precipitate. So we've got green precipitates coming out from both. The important detail is this one. In each case, the precipitate is insoluble, so it will not dissolve when an excess of reagent is added. Now, that's the giveaway, because iron 2 and chromium 3 both give green precipitates. However, the chromium 2 is not one that actually stays insoluble. It actually redissolves in the reagent. So the correct answer is iron 2. So they both go, they both get turned to a lovely green color. But there we go. They go to a lovely green color, but chromium 3 will actually redissolve. So the answer is iron 2. Iron 3 forms like a rusty browny type of precipitate, and copper 2 is very, very familiar. It's very rich royal blue kind of color that comes out from that one. So the correct answer is iron 2. So let's go to the next question, which statements about catalysts in chemical reactions is not correct. So you can pause the video. Okay. So with this question, this was really, really confusing. It's nice contrast with question number 18, because question number 18, we had about 70% in our sample get that right, and 10% picked A as the most popular incorrect answer. So 20%, 10 people, 20% in our sample picked A. And 70%, roughly 70% picked C. Whereas with this one over here, question 19, we actually had less than 40% actually picking the right answer. The most popular mistake, and almost equal to the number of people who actually picked the right answer, was A. A seemed to be the most popular response, followed by D, and then very few people actually picked C. But 22% picked D, 33% picked A, that's 1 in 3, and just less than 40% picked B, and B was the right answer. So if we just have a look at B and try and exclude any of the kind of water is wet type of responses, statements about catalysts and chemical reactions is not correct as well. You've got to remember that this is a big not correct. Well, which one is correct? That one is correct. So that one is actually a correct answer. That's true. Okay, so we could just put a true there. Catalysts increase the rate of reaction. Yes, that's true. Catalysts lower the activation energy. Yes. A slightly harder point for people to recall. It's not easy to revise activation energy. You have to actually know what activation energy is. So the one that's the imposter is B, part B. Catalysts increase the energy of the reacting particles. No, that is not the case. The main thing that you would kind of tend to think actually increases the energy is this thing called temperature. Okay, temperature actually increases the energy of reacting particles. They store more kinetic energy inside them. Right, so our final question for this video is question number 20, a lovely rate of reaction question, okay? And you basically look at something like this and you think there's a huge amount of information, okay? But it wasn't too bad a question. 70% of the sample that we had picked the right answer, and B was actually the most popular mistake, with 20% of our sample picking B. So if you want to pause it, have a go at it. So student investigating rate of reaction. So you've got a gas syringe, so there's clearly a gas that's coming out from this reaction. It is actually carbon dioxide, but you don't need to know about that. Marble chips is calcium carbonate, and you've got hydrochloric acid. You're leaving calcium chloride as a solution inside there, and the carbon dioxide comes off, and the water stays as well, the water product. So which changes slow down the rate of reaction? So slow down is what you're actually looking for. So you put that as a down. Temperature of acid, that will actually increase the rate. Concentration, that will actually increase the rate. The surface area of marbles will increase the rate of reaction. So that's if you actually have an increase in temperature, you get an increase. Increase the concentration, you get an increase. If you increase the surface area, you get an increase, right? So, and what we want is we want stuff that actually slows down the rate of reaction. So we're not looking at D for a start, because D includes a response where you're actually increasing the rate of reaction by increasing the temperature. Actually has increase for all three, so that's the first one that you should actually exclude. If you increase the temperature, you increase the rate of reaction, so C is out. So it's between A and B, and between A and B, that's the odd one out, so it can't be B, it has to be A. A is the right answer. Now, interestingly, you have to get used to phrases like slow or fast rate of reactions, but Cambridge actually prefer you to actually give changes in rate of reaction in terms of increase or decrease, because rate of reaction is actually a number. Rate of reaction is actually a number with units. And that's our final question for this video for part 2. And please join us for part 3. We'll give you more insight, and we'll really dissect and break down these questions for you to get the best grades in Cambridge iGCSE. Thank you very much for watching, and see you in part 3.